Good morning everyone, my name is Marc Moya and here we're going to present a demo coming from the project 6G Data Driven consisting in a deterministic networking, where we are going to present a use case that use all the innovation that we develop in 6G Data Driven in order to increase the reliability of the 5G network and also to bound the latency, to control the variation of the latency in this network. The deterministic networking is built in collaboration with Gestamp, that is a photonic collaborator, and they are working in a concept that's called flexible industry, where they are willing to deploy a new premise or a new production line in weeks instead of months. This deterministic networking demo is built on top of the standardization done by IEEE for the time-sensitive networking. In that standardization, they are trying to improve the determinism of fixed networks. And here we are bringing this concept and work and integrate it in the 5G networks. For that, what we have to do is not only to synchronize in time the elements of the 5G network and the users of the 5G network, but also we present TSN translators that are in the both sides of the 5G network and allows to integrate the 5G network as TSN bridge. In order to contribute to flexible industry, we are going to present the first step of virtualization of the industry. And here you can see two big differences regarding the current state of art. First, all logic is virtualized and is running on top of code servers. And the second change is that the elements of the industry are communicated using wireless network, and in this case using 5G network. The target architecture for this use case is to have all logic in the cloud and to deploy only the physical elements required for the manufacturing industry and then interconnect those elements through 5G network. We need to keep in mind that this deployment is very complex. As you can see, there are a lot of mobile elements, like 8GBs for example, and there are a lot of fixed elements, and all of them has to be interconnected and also interconnected with the logic. In this demo, we're going to set up three requirements on the network. First is the jitter, that basically is the variation of the latency, and we are going to require a variation of less than 1 millisecond. Also, we put a requirement of packet order, because any packet that is received in this order will impact in the working of the elements, and also we are going to increase the packet loss. For this use case, we are going to use a non-public network deployment. This kind of deployment fits perfectly with the demo that we are going to show, as we are deploying in the factory only the elements that are required. And in this case, we deployed the 5G, new radio, and the user plane. And we interconnect this non-public system through a public network that in this case is deployed at photonic. With that, we minimize the kind of elements that we deploy in the factory, and we allow the communication between, for example, the robots and the virtual logic control. Also, this NPN system includes TSN translators in the device side and in the network side that will implement all the TSN and deterministic features. And here you can see the real picture of this portable system that can be deployed in any industry. Then we are going to start with a demo of the use case working in a vanilla 5G system. In the top left of the dashboard, you can see the jitter in the origin. This means that the element, in this case a robot, is sending one package every 10 milliseconds, but there is a variation of some several hundreds of microseconds in the origin. In the top right, we see the KPIs in destination. Here we can see that in in origin we have hundreds of microseconds. In the destination we have several milliseconds of jitter as we pass through the wireless network provided by the 5G. Also, we are monitoring the ordering of the received package. In the bottom, we have some KPIs of the 5G network, like the average of the one with LE and also the throughput. The use case seems to work normally. We only have some high destination jitter, but if we are not protecting the traffic, what happens is that some background traffic can impact in the work of our use case. So now we are going to introduce background traffic that will compete for the same resources that our use case traffic, and then we are going to see that now the one with the LE of the messages sent by our elements are impacted in the latency, and then we have disorder and packet loss. So what we can conclude here is that our use case doesn't work in a vanilla 5G, and we need to improve the deployment. The first thing that we are going to do is to activate some TSN features that we implemented in the TSN translators, in the device side, and also in the network side. The first one will be a synchronous schedule that we implement in the TSN switch and will help in the run slicing. Currently, what we support commercially is a slicing of the run resources, and here we have an example using this use case when we have a public assignment of a spectrum of 100 MHz, and we reserved the 20% of those resources for our use case. On top of that, we can improve this slicing by introducing a synchronous scheduler. Here, we take advantage of the kind of traffic that the industrial elements are generating, and as we know that they generate one message every 10 milliseconds, what we are defining here is that when an industrial element generates this message, we are going to prioritize the TSN traffic, and when we don't expect the TSN traffic, we are going to send the background traffic. With this, every time that we expect a TSN message, we will book the resources necessary to forward that messages without impacting the latency. And here we have this feature working with our use case. Okay, so we can see the original jitter of the traffic, several hundreds of microseconds, and here we can see that if we introduce background traffic, the latency is not impacted. Okay. Now we also have an adaptive reinforced learning agent that will try to optimize this feature, because you can see here that all the TSN packages are buffered, and this is because the time that the element is sending the message is not synchronized with the time that the 5G network expects the message. So using a small reinforced learning mechanism, we are going to minimize the buffer time of the TSN traffic, we are going to minimize the queue rate of the TSN traffic, and then we are going to avoid the impact in the latency for this use case. And now here you can see that the reinforced learning mechanisms converge. There is no impact in the latency of the TSN traffic, as the window is synchronized with the time that the element sends the message, and the traffic is protected, so any background traffic will no impact. This protection is done in the ingress of the 5G network. That means that it's done in this device side TD. But what happens if we want to do something similar in the other sides of the network? The problem here is that we cannot synchronize the time where we expect the message because we are going through a wireless network where the variability of the latency is higher, so it's most difficult to synchronize that. So what we can do here is to use the jitter feature. And in this case, we are going to use the jitter feature based on the modeling that we have in our digital twin of this kind of traffic. So the idea is that using the system response that we know from this kind of traffic, we're going to train a deep reinforcement learning that will be able to reduce the original jitter of the traffic to almost zero for the TSN traffic, for the traffic from the gestamp elements. The requirement in the live demo will be to reduce it to less than 1 millisecond. And here we can see the jittering working. So as the other demos, we introduce one message every 10 milliseconds with a jitter of several hundreds of microseconds. And here you can see how the jittering is working. So basically the jittering is buffering all the TSN traffic and will try to forward those messages with the same jitter that was introduced in the 5G system. So here you can see how the destination jitter is reduced, and you can see that is less than 1 millisecond. In fact, it's less than a half a millisecond. So we are meeting the requirements. The problem is that we have a big impact in the latency. As you can see here, we are starting with 20 milliseconds packet delay budget, but again, we have an adaptive system based on reinforcement learning that will try to optimize the impact on the latency. So in this case, it's quite different to the previous one, because here we are not trying to minimize the buffer time, because if we minimize the buffer time to 0, we are not going to do the jitter. So here we are going to try to minimize the buffer time, but without minimizing the QE rate. And in this case, you can see that the reinforcement learning algorithm converge. We minimize the impact on the latency. We are only adding 1 or 2 milliseconds to the latency, and we are guaranteed that the destination jitter is less than 1 millisecond. This mechanism can be improved, and we presented a paper called Smart Jittering using Network Digital Twin, where we are not using timestamp on the package, and instead of that we are training a deep reinforcement learning agent with the information that we have in the Network Digital Twin, and then this agent, only with the information that it has in the translator, that basically is the inter-packet arrival and the forwarding time of the previous packet, only using this kind of information is able to jitter the traffic. And you can see here where we present the original jitter in the uplink of our system, and then using different methods we are able to reduce the jitter to less than 1 millisecond. So, in summary, we are demonstrating in this demo that TSN can bring enhancement in the 5G system in order to improve the determinism of the traffic, and also improving on the other aspects, like for example the spectrum sharing. We build all the TSN capabilities on top of existing features. We are using IP-based video session, we are using traffic classification that already exists in the UPF, QoS, and other mechanisms already implemented in the 5G. So that means that we can offer TSN capabilities without waiting to a standard TSN integration. For example, we don't need a commercial UI supporting TSN. We can work with our translators with the standard UIs. And that's all. Thank you for your attention.